Should I start?
Yes.
Okay.
So I'm pleased to introduce Professor Manny, and in his second he'll start the first in the series of 3 talks on hyperbolic fields of groups and spaces.
Right. Well, I guess in some sense it's the second of 4 talks, but it's the first of a sort of separate sequence of 3 talks. Where I want to talk. So I want to talk specifically about Dane filling of groups. So anyway, thanks again for having me. For those of you who weren't here, I guess you can hear me say thank you again. But I enjoy being here. Dane filling of groups. So let me just recall the sort of the general picture from 3 manifolds. The thing that we're generalizing, though I'm not going to talk until maybe the very end about how we're generalizing it. So just the sort of operation, so the topological operation, and this will be a little bit of repetition for some of you. Of Dane filling. So we're going to begin with some compact 3 manifold M with boundary of M equal to a torus. This is slightly different from the way I phrased it last time, but we have a compact 3 manifold M with boundary a torus, and so I can get a closed 3 manifold by gluing on a solid torus. So say we'll write M of gamma by gluing on a solid torus. What's a solid torus look like? It's a 2 disk times a circle, so that the curve boundary of 2 disk across a point, say 1, is identified with the circle gamma in the boundary of M. So the cartoon picture is as follows. I have some 3 manifold with torus boundary M. So one thing that you can think about is, so e.g. we could have M equal to S3 minus a neighborhood of a particular knot, and it doesn't really matter which knot I pick, but I particularly like this one. So that's some circle in S3. I want to actually just remove an open neighborhood, small open neighborhood of that, and then I'll be left with a 3 manifold that has a single torus for a boundary component. Now when I want to Dane fill that, what that means is that I'm going to be gluing on a solid torus like this according to some homeomorphism of the boundary. So I'm going to choose i.e. we're going to choose a homeo phi from the boundary of the the solid torus to the boundary of M. And there's a special curve on here, mu. So this is, call this mu. So the inside shouldn't be yellow, but it does bound a disk, which is the point I was trying to make, I guess, with those hash marks. And I'm going to choose some homeomorphism so that that's glued to maybe this curve here. That'll be my gamma. So it's not obvious, but it is true that so this M of gamma is going to be this union after I do the gluing. So it's not obvious, but it is true that the homeomorphism type of M of gamma depends only on that yellow curve gamma. And it doesn't depend really at the homeomorphism. That basically doesn't quite determine the homeomorphism, but it will determine the homeomorphism type of the filling. So this M of gamma is called a filling of M. Now, so last time, and I'll recap this later, but let me just say that the Thurston hyperbolic Dane surgery theorem and also the 2π theorem that I talked about before. So this says that for most gamma, if M, take the interior, was hyperbolic, then so is the closed manifold M of gamma. Okay. And this, the exceptions to the conclusion of this theorem, the exceptional fillings, if you like, are, I think, probably what Cameron Gordon's going to talk about for a few lectures in a couple of weeks here. So he's going to talk about sort of the opposite of what I'm talking about, generalizing in some sense. He's talking about the exceptional fillings. So, but most of the time, if you start with something that's hyperbolic over here, you fill it in somehow, you're going to get something that's closed and hyperbolic. All right. Well, I don't want to talk about Dane filling of spaces so much in these next 3 lectures. I want to talk about what it means to Dane fill groups. And so what's the thing to focus on is what's happening here with the fundamental group. So notice pi1 of M of gamma is equal to the quotient pi1 of M mod out by the normal closure of gamma. And so the kind of group theoretic content of this statement is that most ways of adding a peripheral relation leave you in some sort of negatively curved setting. So, well, I won't write that down because that's a little bit too vague. But I'll hopefully by the end of today's lecture you'll see what the negatively curved setting is. So both of these groups have some negative curvature properties. So this thing right here, this is an example of a hyperbolic group. So I'll define that in just a little bit. And this thing over here, this is an example of a relatively hyperbolic group. And the relation that I attached lies in the peripheral subgroup of that relatively hyperbolic group. So what I'll do today is define what hyperbolic and relatively hyperbolic groups are, and talk about their sort of peripheral structures and give some examples and that sort of thing. Which will be examples, all these examples will be examples to which the group theoretic version of the Dane filling theorem will apply. So this is the picture that I'm trying to generalize. Just maybe pause for questions. That's supposed to be the sort of overview part. Yeah.
Another group of M is hyperbolic and another group of M gamma is relative. Is that the other?
Oh, did I get it backwards? Yes, I did. Sorry. Right. Okay. So this is actually, this one's a hyperbolic group. And the fundamental one group of M is a relatively hyperbolic group. Thank you. Yeah, pi 1 of M is relatively hyperbolic. Right. And then I did some sort of operation. I added peripheral relations to get pi 1 of M of gamma, and this thing is actually hyperbolic. Okay, but I haven't defined either of those yet. But yeah, that's. Thank you for pointing that out. Okay. All right. So let me next define what I'm talking about hyperbolicity and relative hyperbolicity for groups. Oh yeah. So before I do that, let me just recall what it means for metric space to be Gromov hyperbolic. So this is just Gromov hyperbolicity. Gromov hyperbolic spaces. What's the point? So let's let X be a geodesic metric space. And by that I just mean that you can measure distances between points by taking the lengths of paths that go between them, and the distance is the infimum of those lengths, and that infimum is realized by some path, and that's called a geodesic. So X is a geodesic metric space, and we'll let delta be a triangle, a geodesic triangle, though what I'm going to say kind of makes sense. In any case, a geodesic triangle in X, so meaning it's just a union of three sides. We've got X, Y, and Z. So this triangle is said to be delta slim. Right, and so we're going to let delta be a positive number. Or I guess it could be 0. We'll say it's positive. So then delta is, capital delta is little delta slim if each side is contained in the delta neighborhood of the union of the other two sides. Okay, so for example, this triangle is delta slim for delta about 4 inches, right? So we just take the union of these neighborhoods, and it should cover the other side. And so, well, I showed you that this side was contained in the delta neighborhood of the union of these two. I need to check for the other two sides as well, that each of them is contained in the delta neighborhood of the union of the other two. All right, so every triangle is delta slim for some delta. You just take delta equal to the diameter of the triangle, right? But the nice property that a space might have is that delta doesn't depend on the triangle. So we say that X is delta hyperbolic if there exists a delta so that every triangle, and I just mean geodesic triangle, in X is delta slim. So for example, if I have a tree, then that's going to be delta hyperbolic for any positive delta, because triangles are just tripods. So x equal any tree. So then if I have 3 points in a tree and I make them into a triangle, it's always going to look like a tripod. So any side is contained in the 0 neighborhood of the other two sides. So, or x equal to the hyperbolic plane. And so this is something you might have to think about if you haven't seen it before. So if you haven't seen it before, then the exercise is to work out delta. So sort of here's a hint. The biggest triangle you can draw is an ideal triangle. And there's some delta that works for that. Sorry, some of that should have been yellow. Okay. So more generally, if I take a simply connected Riemannian manifold, complete simply connected Riemannian manifold of negative curvature, and curvature bounded above by a negative number, then that's going to be delta hyperbolic for some delta. It's because I can compare triangles there to compare it to triangles in H2. So, say pinch negative curvature Hadamard manifolds. Something I talked about last time, cat-1 spaces. So that's just, so the cat-1 condition is saying that triangles are no fatter than triangles in hyperbolic space. So it's going to follow immediately that since hyperbolic space is delta hyperbolic for some delta, cat-1 spaces will be hyperbolic for the same delta. It's okay if you don't know what these are. They're probably not going to come up very much, but it gives you a source of examples. Okay, so so these are spaces that on the large scale have participate in some kind of negative curvature. So they look large scale negative curves. Small scale they may look very bad, very weird. They could just be graphs with huge holes in them. But those holes are, well, they're huge, but maybe small, delta is going to be much bigger than the size of the holes. So delta is just some finite number. It's okay if it's really enormous. It just needs to be universal over all the triangles. So something that's going to be kind of important is that so if you've studied the hyperbolic plane, you know what the isometries look like. They're divided into three types. There are hyperbolic isometries that preserve an axis. There are elliptic isometries that fix a point. And there are parabolic isometries that kind of do neither and move some points smaller and smaller distance and fix a kind of point at infinity. Right? There's a similar classification of isometries of a hyperbolic space, of a Gromov hyperbolic space. So if there exists a, sorry, I said this wrong. So I should have said X is delta hyperbolic if every triangle in X is delta slim. So that's what I'm defining there. And then it's Gromov hyperbolic if there exists a delta. Okay, this is named after Gromov, who first started studying these things. All right, so isometries of Gromov hyperbolic spaces. So there's sort of three classes. And they're the same as the classes that you see in H2. So in H2, so if I have phi from H2 to H2 an isometry, I can think of the upper half space model of H2, and I can think that phi of z is really given by some az plus b over cz plus d. So I'm thinking of these as complex numbers, right? And where I've got a, b, c, and d, this is in SL2R. Okay. And minus the identity doesn't do anything. So in fact, these are all the isometries of H2, except for the orientation reversing ones. So it's all the orientation preserving isometries of H2, which you've probably seen this before. And then you can class them into elliptic, hyperbolic, and parabolic according to just the trace. So the sort of thing you want to think about here as an example of an elliptic isometry, something like that. So this is just going to rotate everything around this point I by some angle. Hyperbolic things are things with bigger trace. So I've got, so for example, 2, 0, 0, a half, parabolic, something like 1, 1, 0, 1. And what, so this is H2, but what do these mean in the general delta hyperbolic space? So an elliptic isometry is one that has a bounded orbit. So in H2 it has to have a fixed point, but in general we don't need to have like nice local convexity properties for the space, so it's just going to mean that it has a bounded orbit. Hyperbolic if I look at the map from Z into X, so I've got some isometry. So I've got phi and isometry from X to X now. And now if I think about Z going into X by, so let's call this F, by F of n is equal to phi to the n of X. So I fix some particular point in X. This should be a what's something called a quasi-isometric embedding. So let me write down what that means. So i.e., there exists constants k and c, so that if I look at the distance in X between f of n and f of m, then that's then it's sort of Lipschitz in the large, so it's at most some constant k times the difference between m and n plus maybe a constant c, and it's least 1 over k times the distance between m and n, and then maybe minus a constant c. In fact, I really just, if I'm just looking at z, I don't need this constant c, I just need this constant k. But this is kind of maybe useful to write down the definition of what's a QI embedding. So in general, if I have some source metric space, so here I've just replaced that with the distance between points in the source. And here's the same thing, distance between points in the source. And it's saying that that distance under the function is distorted at worst by a bi-Lipschitz function in the large. And on small scales, no condition. Scales smaller than c, anything could happen. Doesn't have to be continuous, what have you. So that's what it means to be hyperbolic. And then the parabolic isometries are ones that kind of fix a single point at infinity, but are not elliptic. So points at infinity, what am I talking about? If you think about H2, maybe rather than define it, I'll just sort of appeal to your intuition about H2. So parabolic. So unbounded orbits. And what do I mean by an orbit? I mean I look at the set of phi to the nx, so that n is in Z, and exactly one fixed point in the boundary at infinity of X. So there are a number of ways you can think about the boundary at infinity of X. So the boundary at infinity of H2, though, is S1. So if I think about the upper half plane again, then it's the real line union, the one-point compactification of the real line. And so if I think about what does that matrix 1, 1, 0, 1 do, shifts everything to the right by 1. So it's fixing that point at infinity. If I go to the Poincare disk model, you just see that everything is kind of moved around in this direction. But this point at infinity is fixed. So it preserves some family of circles tangent to that point, and those are called horocycles, and something similar to that will come up in just a very short amount of time. Okay. So that's isometries of hyperbolic spaces. So I bring this up because I'm going to define hyperbolicity and relative hyperbolicity in terms of certain actions of groups on hyperbolic spaces. So let's begin with hyperbolic groups.
By the way,
yeah.
what do you mean by elliptic for having a single boundary origin?
It means if I pick any point and look at its orbit, then that's bounded. Yeah. So if I fix x and look at this set, then that's a bounded thing. So here, so for the hyperbolic, if I fix x and look at the orbit, it looks quasi-isometric to a line, and here it looks like something else. Looks like something else. So okay. So the definition is that if so a group G, so this should be a finitely generated group, is hyperbolic if its Cayley graph is hyperbolic for some, or really for any, choice of finite generating set S. Okay, why doesn't it matter the generating set? Well, there's 2 points. So, so one is that is the Milnor-Schwarz lemma, which says that so suppose G acts properly co-compactly on a proper metric space X, so then G is generated by some finite set S in G, and well, it's a little bit stronger than this, but I'll just say X is quasi-isometric to gamma of GS. Now, what's a quasi-isometry? So, a quasi-isometry is a QI embedding with quasi-dense image. Okay, I don't know how many people know this language in their bones and how many of them have never seen it before. So this is a QI embedding, right? So where in general I should replace this by the distance in the source. Okay, so I say that I'm going to have a quasi-isometric embedding, say from X to gamma of GS. Some map that on the large scale looks bi-Lipschitz, And to say that it's quasi-dense means that every point in the target is within some constant of the image, right? So I hit almost every point, right? If I blur my eyes, it looks like I hit every point. Okay, so this here, what this symbol is saying is that there is a quasi-isometry from X to this K-graph. Now, so that's one fact. So a second fact is that if you have two geodesic spaces and one of them is delta hyperbolic, then so is the other. Well, for maybe a different choice of delta. So we'll just call this a proposition, and you can look up the proof, is that if I have X, Qi to Y, where X and Y are geodesic spaces, and X is Gromov hyperbolic, then so is Y. Okay, so put all that together. If I think about a group, it's acting properly and co-compactly on any of its K-graphs. If I have a finitely generated group, if I have a finitely generated group, it's acting properly co-compactly on any of its K-graphs. The K-graph is a proper space, meaning balls are compact. So that's what proper means. And so the Milnor-Schwarz lemma applies. And so it's going to say that if one K-graph of G is delta hyperbolic, then all of them are. And moreover, it tells me why. It tells me that if I have a group that acts properly co-compactly, say on Hn, then its K-graph is going to be hyperbolic, because its K-graph is Qi to the thing that it's acting properly co-compactly on. So, hence, so if M is compact, negatively curved, then if I look at pi 1 of M, this is a hyperbolic group. Universal cover is a Hadamard manifold of negative curvature, pinched, negative curvature. So that's delta hyperbolic for some delta. And then this says that so is the K-graph. And same for the fundamental group of a compact cat minus 1 space. Okay, so those are some more examples. So other examples that don't obviously come from this construction. So other examples of hyperbolic groups. Free groups. So this says here that surface groups and hyperbolic 3-manifold groups and closed hyperbolic n-manifold groups are all hyperbolic. But also, so most one-relator groups, random groups are hyperbolic if you take, so there's a way to make this precise. If you just take a free group and then you add some relations at random. So in a sense you can make precise with probability 1 you get a hyperbolic group. Okay. And also there's these things called small cancellation groups. If you have a strong enough small cancellation condition, then you get a hyperbolic group. So what this is saying, kind of most groups, well, the random part is saying most groups are hyperbolic. You're unlucky if you get a group that's not hyperbolic. But here's something else that's true. partly you can get this from kind of the classification of isometries of hyperbolic spaces together with a little bit of thought about what it means for the action to be proper and co-compact, to get that if you have a hyperbolic group, it can't contain a z plus z. So it can't contain a z plus z. However, G hyperbolic implies no embedded z plus z. Okay. Now, that is maybe disturbing to some people because, for example, if I look at M equal to S3 minus sort of sufficiently complicated knot, I didn't draw a sufficiently complicated knot. The figure 8 knot, the one that I drew before. There it is. Okay. So if I look at that, that supports a metric of constant negative curvature. So that's a hyperbolic manifold, right? So this is hyperbolic manifold. But it has a pi-1 injective torus in it. I can sort of draw it kind of encompassing, sort of swallowing the knot here. We kind of talked about this last time as well. Okay. So this torus is pi-1 injective. Okay, fundamental group of a torus is z plus z. So that says that pi-1 of m here is not hyperbolic. So we have some confusing notation. I mean, we have some confusing language here. So let me talk about how to fix that confusion. So this is however, an example of a relatively hyperbolic group. And the point is somehow that in some sense the only obstruction to this group being hyperbolic is this z plus z. It's sort of hyperbolic everywhere else. Okay. We can make that precise. Any questions before? I've been zooming along. Yeah.
If M is compact negative hyperbolic group.
Yeah.
If we compact pi S3 minus that, then we get a compact negative curvature space.
You don't actually. You think you do, but you don't. Yeah. So if you compactify it sort of in the way that I've drawn, like with the yellow torus, then that yellow torus ends up being flat. So it's not negatively curved. So it's a manifold with boundary, with the Riemannian metric on the interior is negatively curved. You're correct about that. But that's not, I guess, not what I mean by a negatively curved manifold. I mean a manifold without boundary. Yeah. So I mean without boundary. Whereas to make this compact, I have to add some boundary. Makes sense. Other questions? Okay, so yeah, what does this mean? This means that if S is a generating set for pi1 of m, then that's going to imply that if I look at the Cayley graph of pi1 of m with respect to S, this is not Gromov hyperbolic. So one way to think about what's going on here is that I have a QI embedding of a Euclidean plane into the fundamental group here, into this Cayley graph. Now if you think about a Euclidean plane, think about triangles in a Euclidean plane. Just take a big right triangle like this, your favorite triangle. Okay, that's delta hyperbolic for some delta. right? I don't know. I can make it work. But if I double the size of the triangle, I'm going to have to double delta, right? I keep making it bigger and bigger and bigger, and the triangle's getting fatter and fatter and fatter. It's not staying uniformly thin like it would in a hyperbolic plane. So you can transfer that statement to the fundamental group of the boundary torus and fit those fat triangles into the Cayley graph as well, using this sort of quasi-isometry between the Cayley graph and a space that it acts nicely on. Okay, so next I want to talk about relative hyperbolicity. So how do we solve this problem? We have this subgraph which can't be hyperbolic. I want to hide it somehow in a hyperbolic graph. So sort of hide any graph in a hyperbolic graph as follows. So I've got gamma is a graph. So I'm going to define H to be the horoball based on gamma. So this is a combinatorial horoball based on gamma as follows. So if I look at the vertex set, this is going to be, well, I take the vertex set of 0 and then I cross it with the non-negative integers. Okay, and now I want to connect that up into a graph. So that my vertex set is much bigger than much bigger than the vertex set of gamma somehow. And I want to put gamma at level 0, and then I want to put sort of more tightly connected copies of gamma at the different depths greater than 0. So how do I define the edges? So there's going to be two types of edges. So if I have a vertex of gamma, then I want to connect Vn to Vn plus 1 for all. So this is for all V in gamma, in the 0 skeleton of gamma, and all n in non-negative integers. So those are my vertical edges. So these are called vertical edges. And then I also have some things that are called horizontal edges. So, and what do? So they're going to connect Vn to Wn when. So it's going to be some condition that depends on n. So if the distance in gamma between V and W is at most 2 to the n. Okay, so you see at level 0, sort of where the second coordinate is 0, I'm just connecting things if they're connected in gamma, right? Second level, I'm connecting them if they're distance 2 apart in gamma. Third level, if they're distance 4 apart in gamma, and so on, right? So kind of the picture, say I have some very small graph like this. So I begin by just connecting these rays. So this is the vertical edges. I guess I should draw all this in different colors maybe. So I'll draw the vertical rays in yellow. And gamma's at the top, it's in white. I want to think of this as something I'm attaching to gamma. So I've got gamma up here at the top, and I've got the vertical rays. And then I have some horizontal edges. All right, so at level 2, things that were distance 2 apart are now distance 1 apart, and now at level 3, well, everything in sight is distance 1 apart. And then in this finite picture, it doesn't change after that. But if I started with an infinite graph, I'd be adding more and more edges at each depth. You see? Sort of making things tighter and tighter together. So this is sort of a combinatorial version of a warped product. So this is a combinatorial approximation to just taking a warped product. So I've got gamma, and then I'm going across 0 to infinity, and I'm using a warping function 2 to the minus t. So this is some sort of warping function. So on the large scale, if I just start with a line, down at depth 1 I have a line, but the distances have on the large scale just been multiplied by a half. And at depth 2 multiplied by a quarter, and so on. So geodesics are going to tend to go down into the horrible and over and back up again. So so what's my color coding? So maybe I've got a vertical, a little bit of horizontal, and then vertical. Okay? So they're very simple. So they don't have to look exactly like this, but they're going to look very close to something like this. Right? And this is going to be a segment of length 2 or 3. So it's an exercise based on this definition to show that H is 10 hyperbolic. You can probably get a number less than 10. It's probably like 2 or something, but I know it's less than 10, so 10 works. What's that? It doesn't depend on gamma, that's the point, yeah. Independent of gamma. So I took any graph at all, and I stuck it inside an infinite diameter 10 hyperbolic graph. And the metric became very distorted, right? The metric on gamma is very, very distorted, but it's not all crushed to a point. I mean, another way you could put any graph inside a delta hyperbolic graph is just cone it all to a point. So that's a finite diameter graph. So it's easy to see that that's the diameter hyperbolic. Okay, so now what's the point? So I'm going to start with a Cayley graph of my group G. I'm going to start with, and I'm going to attach, which is supposed to be relatively hyperbolic, and I'm going to attach a bunch of these combinatorial horoballs to pieces of that Cayley graph. So let's just let GP be a group pair. And in general, I mean, you can allow P to be a collection of subgroups, but I'm just going to have P a single subgroup for everything I talk about pretty much. So we're going to let GP be a group pair where G is generated by some finite set S, and suppose that this subgroup is generated by S intersect P, which is of course then also going to be a finite set. We'll call this set S sub P. Okay. If P is finitely generated, it's easy to just add the generators of P to the set S, and you'll have this extra property. So So the cusp space for the pair GP with respect to this generating set S is built from gamma equal to the Cayley of G with respect to S by gluing on horoballs. Okay. How many horoballs? So choose T, a transversal for G mod P, the left cosets of P. And so if I look at, so I let T be in capital T, and I look at the vertices, so the vertices T, P span a subgraph of gamma isomorphic to the Cayley of P with respect to the generators S sub P. Okay, so that's certainly true if I pick the trivial one, right? But the graph is sort of everything about the graph is invariant under left multiplication. You have this left action of the group G acting by isometry. So it's going to take one coset to another coset, and the graph spanned by the vertices is going to look the same. Always going to look like this Cayley graph here. So let's call this gamma sub P. And so I can let H be equal to H of gamma sub P. And now I want to glue a copy of that onto every left coset of P. So X of GP is defined to be, I'm going to take gamma union, sort of this, I'm going to take this disjoint union of T and T of a bunch of copies of the Cayley graph, not the Cayley graph, of H. And what is the map going to be? So the map is that, so we're going to identifying, so this is H of T. So so level 0 of H of T with TP sitting inside gamma. So I'm doing some identifications here, doing this gluing on. So there's a definition, which is that the pair GP is relatively hyperbolic if this space is Gromov hyperbolic. Okay, so there are a number of different definitions of relative hyperbolicity, and this is one of them. And yes.
What do you mean by transversal?
Oh, I just mean that for each coset, I'd pick something in the coset. Yeah.
Excuse me.
Yes.
The word which is cut from P. Second sentence.
Vertices. The second sentence. By gluing on horoballs, choose T a transversal for G mod P.
The cusp space for GP
Is built. Built. Built from gamma, yeah. I just mean that I'm going to start with gamma and I'm going to glue a bunch of stuff on. So I was thinking of gamma as the sort of the frame, and I'm adding on walls and things. Other questions? Okay.
So 2 points in gamma p can be very far in gamma p but close in gamma.
They could in general. That's right. They might be in general. Now, if the pair is relatively hyperbolic, they won't be. So this is a consequence of relative hyperbolicity is that the Kähler graph of the subgroup is actually QI embedded. But yeah, in general, it might not be. Yeah.
So when you're constructing H gamma p, you just consider the distance in gamma p.
That's right. I'm just looking at the distance in gamma p. So you could also look at the distance. So okay, you get another construction if you just start with the distance induced by gamma, and it doesn't really make any difference which one you use. You won't get any. Yeah, the class of pairs that are relatively hyperbolic will be the same. Yeah, that's a good question. That's not obvious, I think, but it's true. Okay. Okay. So this is what seems like a very complicated definition for this concept, but it's really. Let me just point something out. So, which is kind of useful. So note, and again, this is not obvious, but you can prove that if we had G equal to the fundamental group of a one-cusped hyperbolic n-manifold, and if I had P is equal to the fundamental group of the cusp, then the space X of GP is quasi-isometric to Hn. So you really did, doing this combinatorial business, you recovered something that it was at least quasi-isometric to the right thing, right? So I mean, why do I say that's the right thing? So like, why do we think that hyperbolic manifolds should have hyperbolic fundamental groups? Because they're acting in a nice way on this hyperbolic space, okay? Now the action, so this quasi-isometry will quasi-conjugate the action on Hn to the action on X of GP. So they're the same action from the coarse point of view. Okay. What do I want to say? Maybe I'll just say that. So just this, well, okay. I guess it's clear from sort of this fact. So the point of building this space is it's supposed to, the way G acts on this space, if GP is relatively hyperbolic, it's supposed to be much like the way cusp hyperbolic and manifold group acts on Hn. So in particular, these elements in P are going to act as parabolic isometries. They're going to be fixing this sort of pointed infinity of the horoball that you glued on. So if GP is relatively hyperbolic and P, well, let's say little p is in big P, then if I look at P, if I think of P as an action, P is an isometry from X to X, where X is this cusp space, this is a parabolic isometry, or possibly elliptic. So moreover, if I look at G acting on X, this is proper, X is proper, but the action is not co-compact. Right, so if it were co-compact, we would have shown that G was hyperbolic, but G may not be hyperbolic. So what does the quotient look like? If I look at X mod G, this is going to be Qi to array. So just array. So what's it actually going to be? It's going to be array with some roses attached. So a bunch of loops. So and if I have, so you can build a cusp space for G comma several subgroups, and then the quotient will be a wedge of rays. So I look at X of G comma P1 up through Pn, which I have kind of not been talking about, mod out by G. This is going to be Qi to n rays. Let me give you an idea of how hyperbolicity might fail. So if I had two cosets that coarsely had large intersection with each other, meaning infinite intersection with each other, then it would fail. So suppose the set of P so that the distance between GP and P is less than R, or infinite. So suppose it's Qi to a line. Just to draw the simplest picture. So I have this line in P, so this is sitting inside P. And then I have another line over here, which is in GP. And it's not that far apart. And suppose that G, so this is some set that depends on G. So we'll call this I sub G. So G is not in P. Then what's the picture going to be? Well, inside X, you're going to have, on both of these lines, you have this cusp space. So there's another cusp space in the back here. And you have some stripes here, some red stripes. So things are getting closer and closer and closer together. If I think about a geodesic from this point to a point that's very, very far along here, and another point that's very, very far along here, what that's going to want to do is it's going to want to go here. The geodesic from here to here is going to go over to P, way down deep into this horoball for P, and then back up, right? And similarly, the geodesic here is going to go way down deep into GP, and then come back up here. And then there's some fairly short thing there. So now what you can see is that this side of the triangle, if I choose these points very far along the line, is going to, I'm going to need a huge delta to get it in the delta neighborhood of the union of the other two sides. So here's this is not the easiest way to think about this. If you think about a hyperbolic horodisk, so just think about all the points in the hyperbolic upper half space model, where the imaginary part is bigger than 1, bigger than or equal to 1. So take that. That's some metric space. Double it along its boundary. Okay, you can show that that's not delta hyperbolic for any delta. And I've basically got a QI embedding of that into this space. So, for GP relatively hyperbolic, distinct cosets of P have small coarse overlap. Okay. So that's meant to make the following statement a little bit more plausible in one direction at least. So there's so just one example besides hyperbolic hyperbolic manifolds of relative hyperbolicity is the following. So there's a theorem of Bowditch, which is in his paper Relatively Hyperbolic Groups, which I think has finally been published. It was like a fundamental paper in the field for a very long time and wasn't published for some reason. Anyway, so this result is that if G is hyperbolic, then the pair GP is relatively hyperbolic if and only if P is quasi-convex and malnormal. In G. Okay. Maybe I should say what quasi-convex and malnormal are. So quasi-convexity is a geometric condition. So if I have X geodesic space, Q sitting inside X is lambda quasi-convex if any geodesic with endpoints in Q lies in the lambda neighborhood of Q. So if I draw a geodesic between 2 points in Q, I can't get too far away from Q. So there's some universal bound. And so it's quasi-convex. So you just say that Q is quasi-convex if there exists such a lambda. So Q is quasi-convex if there exists such a lambda. Now, quasi-convexity in the group theoretic setting. So P, so G is hyperbolic, so it's finitely generated group. So I just pick any Cayley graph, and now I think of P as a subset of that Cayley graph, right? Every element of P is a vertex of the Cayley graph. So that's some subset. It's either quasi-convex or it's not, right? And if it is, then we say that the subgroup is quasi-convex. Okay. So P, oh, and I should say almost malnormal here. Sorry. Almost malnormal. So P is malnormal if whenever I have G in G minus P, that implies that P intersect P conjugated by G is the trivial subgroup. Okay. Almost malnormal means that it's a finite group. So instead of being trivial. But in particular, if I take a torsion-free hyperbolic group G, then a pair GP is going to be relatively hyperbolic if and only if the subgroup P is quasi-convex and malnormal. Okay, so this ends up being extremely useful for applying what I'm going to talk about next time, the Dane-Filling theorem, to hyperbolic groups. So not to this wider class, but just to hyperbolic groups themselves. Because hyperbolic groups tend to have lots of quasi-convex subgroups. They're not always malnormal, but there are tricks you can do to turn non-malnormal ones into malnormal ones. questions? So to give an example of a quasi-convex subgroup, if you have, so what's your favorite example of maybe a free group? So if you have a free group, then any finitely generated subgroup will be quasi-convex. All right. If you have a manifold group, if you have a hyperbolic manifold group, and you look at the subgroup corresponding to a totally geodesic submanifold, so that's going to be quasi-convex. If you look up the universal cover, you can think about this. The map from the Milnor-Schwarz theorem is basically says, take a point, and now what's the map from the Kähler graph to the space? You just take the point to its image under the group element. So a vertex of the Kähler graph is a group element, so I take G to Gx, where I fix my x. And so if I pick that point, I can pick the point wherever I want, so I can pick it on the so I have this totally geodesic thing, say an H2 inside H3. I can pick my point here. If I have a closed surface group in here and I look at its image under there, that's going to be almost everywhere in that H2. And so it's pretty clear that that's going to be quasi-convex in H3. Nice thing about working with delta hyperbolic spaces is that quasi-convexity is pretty stable under using quasi-isometries, which is not the case in general, but works for delta hyperbolic spaces. Okay, I think I will wait to state the relatively hyperbolic Dane filling theorem until next time and stop there for today. Okay.